so we will continue our subject with PageRank. So the PageRank algorithm, that iterative solution that we have seen, is the original PageRank algorithm that Google is using around the same time that algorithm was invented. Another scientist who was not aware of what the other guys were doing came up with a different algorithm for computing PageRank called hubs and authorities, or hits. And so we will look at how that works. This particular algorithm did not become profitable. The first one that we have seen become profitable and used. Another thing we'll talk about is the spammers. So these link spammers that are creating spam farms that try to fool the PageRank and increase the PageRank for a specific page of their choice. And then we will see a little bit about the size of the matrices and graphs that the search engines have to deal with when they compute these PageRank. So, what is hits? So hits has introduces two other concepts that are used to compute the importance of a page, which are hubs and authorities, and they also follow a similar recursive method as the PageRank that we saw earlier. So what is a hub? So this hub and authority we'll try to measure those. So these are measures that help us to determine the importance of the page. So the hub is a page that has links to authority pages. And authority pages are pages that are important, where a lot of information can be found. So these are pages that have a lot of links with important information on them. This could be, for example, a course website, a course homepage that has the links to all of your lecture materials and exercises and preparing for exams. So that is an authority page. A hub is a page that shows links to many authorities. So a hub could be the department website. So the department website has links to all the faculty websites, which have the course websites on them with the information about the courses, the PowerPoints and exams and exercises. So an example of a hub would be the department website that has links to many authority pages, and the authority page is, for example, the home, the course web page or syllabus. If we think of it with this type of concept, we are again introducing the notion of the importance of the page. So we will express that in the form of a matrix again. So we will have matrix A, and a position ij of the matrix is a 1 if the page I links to page j, and it's 0 if it does not link. And this is similar to what you have in your exercise today for the PageRank. So there is a matrix that shows whether page I has a link to page j or not. In reality, we have not the 1 and the 0, but we have 1 over n, depending on how many links that page has to other pages as well, including those two, I and j. So this is a matrix that we're considering for hits, either 0 if there's a link, or if 0 if there's no link, or 1 if there's a link. The transpose of this matrix, which is to switch the rows become the columns and the column becomes the rows, the transpose of the matrix is similar to the PageRank matrix that we have seen earlier. That was matrix M, and that's because the PageRank matrix had the similar information in the rows that this matrix has in the columns. So if we take the transpose, then this will be showing pretty much the same information. The only difference is that here we have ones, and in the page rank we had 1 over n, depending where n is the number of links that this page has. So here it uses column vectors. We will call it we have 2 vectors, one for hubs or hubbiness of the site and one for authority. So these are 2 measures that will show how likely this website is to be a hub site and how likely it is to be an authority site. So the degrees of which each page is a hub or authority respectively. The way we will compute these measures is very similar to the way we computed the page rank earlier. So it's an iterative solution. Going back to our example from 1836, where we have 1839, where we have the web consists of 3 websites, Yahoo, Amazon, and Microsoft. And if we are to compute this hubbiness and authority, then our matrix will look like this. Yahoo has a link to Yahoo, yes. Yahoo has a link to Amazon, yes. Yahoo has a link to Microsoft. We added this link now. This link was not here earlier. So with the previous examples, here would be a 0, but now I have a 1 because we created a new link from Yahoo to Microsoft. Amazon has a link to Yahoo, so there's a 1 here. Amazon has a link to Amazon, no, it doesn't link to itself. And Amazon has a link to Microsoft, so there's a 1. And that's how this matrix looks like. So what we will do here, we can multiply this matrix with itself. So we can take powers of this matrix and we can use the transpose of the matrix, or we can multiply them with some specific factor or constant. So because if we keep multiplying them by themselves, their values will grow exponentially. If we don't want them to grow that fast, we can reduce the growth by using some scale factors, lambda and nu, that's for the hubbiness and authority respectively. So if we are to compute this hubbiness and authority, let's H will be the column vector measuring the hubbiness, and A will be the column vector measuring the authority of each page. So we will multiply our matrix by this vector. And use the scale factor. So for the hubbiness, we will multiply the matrix by the authority vector and use this hubbiness scale factor lambda. For the authority, we have the opposite thing. We will multiply the transpose of the matrix A by the hubbiness vector and use some scale factor nu for that. And again, the reason we use the scale factor is so that we're not exponentially growing as we keep multiplying this matrix, because this is an iterative. We're gonna keep doing this multiplication until we converge. So this is an iterative solution, the same as the page rank. So hubbiness becomes the scaled sum of authorities of successor pages. So how many links it has two other authority pages. And the authority scale sum of heaviness of the predecessor pages. This means pages that point to the current page that were considered. So how many humps point to our page? If we are to solve these equations, what we're interested in is H and A. So what will happen is lambda times mu, the two factors, multiplied by the two matrices multiplied, and times the heaviness vector. And for the authority we have the same thing, except it's A transpose multiplied by A. Here it's A multiplied by A transpose. And that's a different result. So the way we will compute this is by iteration. So we will continue to multiply until we converge. The scale, what kind of number we will choose for this lambda and mu. So this is up to us, but the only reason again we use the scale is to prevent obtaining some huge numbers as we keep iterating and multiplying like that. As long as we pick some number, it's okay. So we just need to choose some scale factors there as we keep multiplying like that. Let's see how this multiplication looks like. We will start again with the vector of all ones. So we are giving equal importance to all of the pages in terms of authority. So now we are computing the authority of Yahoo, authority of Amazon, authority of Microsoft. Start with all ones. This is our equation. This is what we are computing here. And to replace in the equation, so we will use all ones. This is the matrix A that tells which page has a link to which page. That is the transpose of the matrix. That is the rows or the columns. A row is column here. A multiplied by A transpose is this matrix. A transpose multiplied by A is that matrix. So for authority, we will use A transpose by A. So we are using this matrix right here. We're multiplying it by that vector to compute the authority. So when we multiply the first row, we will get, when we multiply for Amazon, we will get the number 5. I mean for Yahoo, we will get the number 5. For Amazon, we get 4, and for Microsoft 5. And that's because we have 2 plus 1 plus 2 is 5. 1 plus 2 plus 1 is 4, and 2 plus 1 plus 2 is 5. So next, we will use this vector to multiply the matrix with, and when we do that, we will get these numbers. So what I want to show is that the numbers keep getting bigger and bigger and bigger, and this is when we will converge. This is for the authority. Now for the heaviness, we will use this matrix because this is A times A transpose. Again, start with a vector of all ones, multiply this vector by this matrix, and this is what we get. 6, 4, 2, because this 3 plus 2, 5 plus 1, 6. 2 plus 2 is 4, and 1 plus 1 is 2. This is what we get here. Next, we will multiply this matrix by this vector, and that's the numbers that we get. And when we converge, this is the result. So this result is showing that Yahoo is the most important page out of the 3. So it has the highest hubbiness. The next is Amazon, and the next is Microsoft. That is because Yahoo has the most links coming out of it to other pages. If we go, because remember, the hub is a page that has a lot of links to other authorities. Because if we look back to our graph here, we will see that out of these, Yahoo is the one that has the most links coming out of it because it has 1, 2, 3 links. The others have 2 and 1. So Yahoo is the most important one, Amazon is the next important one, and Microsoft is the least important one. This is according to the hubbiness that we calculated here. So in order to keep components within bounds, we need to use these scale factors, because if we don't, if we're just using the original matrix A, it's okay. But if we're using the multiplied matrices A plus A transpose, the matrices are a lot more dense. They have a lot more ones in them. And if we keep multiplying them, we will get much bigger numbers. Our numbers will grow exponentially. And that is why we need to use these constants to try to decrease the growth of our multiplication. So we can choose these parameters. They can be varied also at each iteration. So what we can do is start with all ones, multiply by the transpose matrix to get the first authority computation, and next we scale and multiply by the original matrix to get the hubbiness. This will give us a better result without growing these multiplied numbers too much. We don't want to compute the A times A transpose and A transpose times A first, because as we keep iterating, then we will have some issue with numbers growing so fast. And again, as I mentioned, the reason for that is because these matrices have a lot more ones than the original matrices. The matrix for PageRun is very, very sparse. It'll have a lot of zeros and very few ones.